Welcome back to Talk Tensors, the show where we unpack the latest and greatest in machine learning research. Today, we're going a deep dive into a paper that has the potential to really shake up the world of game AI and maybe even beyond. It's called VLMs Play StarCraft II, a benchmark and multimodal decision method.
It's a fascinating paper, really intriguing how it takes a totally different approach to building AI for StarCraft II. Instead of simplifying the game, they've created a system called VLM attention that can actually process what it sees and use natural language to make strategic decisions, just like a human player.
So instead of feeding the AI abstract data, it's actually looking at the screen, taking it all in, and reacting in real time. That's a huge leap from how most game AI works, isn't it?
It is, a big one. Up to this point, most game AI has depended on handcrafted rules or policies trained on these simplified versions of the game. But this paper proposes a much more human-like approach. The AI gets visual input, RGB images just like you and I see, and then it uses a vision language model to make sense of it all.
So hold on, it's not just spotting the units and where they are. It's actually understanding the entire situation, the flow of the battle, what's dangerous, what's not. And to do all of this, it uses natural language. That's the part that blows me away.
Absolutely. Using natural language is one of the most groundbreaking parts of this research. The VLM attention system works with natural language prompts, basically asking itself questions in plain English to guide its decision-making.
So it's like, it's asking, okay, which enemy is the biggest threat right now? Or where's the best spot for my siege tanks? Like it's having a conversation with itself using language to come up with strategies. Amazing.
Exactly. And the researchers found that this approach leads to a level of strategic thinking that's really rare in game AI.
Before we get into the nitty-gritty of how it all works, I think it would be helpful to take a step back and look at how we got here. StarCraft II has been a benchmark for AI research for years, with some major breakthroughs along the way. Can you give us a quick rundown of some of the key milestones that led up to this paper?
Definitely. StarCraft II, it's a tough nut to crack for AI. It's super complex, everything happens in real time, and there are just so many possible moves. Early attempts at StarCraft II AI relied on rules that programmers set up for specific situations, but those were too rigid, couldn't handle unexpected stuff. Then came machine learning. Reinforcement learning, in particular, showed some real promise in training AI to play at a high level. And then we saw a huge breakthrough with DeepMind's AlphaStar, which achieves superhuman performance using a mix of supervised and reinforcement learning.
AlphaStar, that was a game changer, but it relied on a very engineered approach, needed tons of data and computing power. What sets VLM attention apart from those earlier methods, especially AlphaStar?
Well, one key difference is that even though AlphaStar was incredibly powerful, it still relied on a simplified view of the game. VLM attention takes a more human-like approach, processing the visuals directly. This means it can learn straight from what it sees, potentially needing less complex feature engineering, and being able to adapt to new situations faster.
So it's not just about winning the game, it's about understanding and playing the game more like a human would. That's a pretty profound shift, wouldn't you say?
Absolutely. It opens up really exciting possibilities for creating AI that can interact with the world in a much more natural and intuitive way. And the applications go way beyond games. The techniques from this paper could have a big impact on fields like robotics, autonomous driving, even medical diagnosis, any area where understanding what you see and making good decisions is critical.
I can't wait to explore those possibilities in more detail. But first, let's get into the heart of this paper. What are the main components of the VLM attention system, and how do they work together to enable the AI to play StarCraft II so well?
At its core, VLM attention has three main modules: the VLM attention mechanism itself, the knowledge integration module, and the dynamic role assignment module. Each one is crucial in allowing the AI to perceive, understand, and act strategically in the game.
Okay, so let's unpack that a little. What's the first piece of the puzzle?
The VLM attention mechanism is what processes the visual information and extracts the important bits. It uses a powerful vision language model that's been trained on massive datasets of images and text. This lets it recognize objects, understand their positions, and even figure out what other players might be planning. Think of it as the AI's eyes and brain, letting it see and understand the world of the game.
So before we went to right before that last little bit there, we were talking about the core components of VLM attention, and
Yeah.
specifically that first part, the VLM attention mechanism. This is how the AI makes sense of the game, like how it sees and understands what's going on, right?
Exactly. This mechanism is all about interpreting the visual input. It's like a super advanced system that can identify each unit, what type it is, where it is on the screen, and even more than that, it can grasp the relationships between those units. It can see formations, predict movements, and even evaluate potential dangers.
Wow, that's impressive. So it's not just seeing, it's comprehending the strategy of the game. It's what makes this all possible.
The workhorse here is a vision language model. It's a type of neural network that learns from both images and text. These models are trained on massive data sets of images paired with descriptions. This lets them link visual features with the corresponding concepts in language.
Ah, so like those AI that can look at a picture and generate a caption that describes it accurately.
Exactly. But in StarCraft II, it goes even deeper than that. The model actually learns the strategic elements of the game, connecting visual cues with their implications for the match. Like it can recognize that a group of siege tanks bunched together means a strong defensive position, or that a bunch of zerglings swarming towards your base is a sign of an incoming attack.
It's like the model is developing this strategic intuition, almost like a human player gaining experience over time. How does it cut through the noise of a StarCraft match and focus on what's really important when everything is changing so quickly?
Well, that's where the attention part of the name comes in. The VLM attention mechanism uses this technique called attention to hone in on the most important parts of what it's seeing. You know, like when you're playing a game, you don't focus on everything on the screen equally. Your attention goes to the areas that need your attention right now, the strategically interesting parts.
Right, I get it. So the model is constantly looking at the visuals and deciding what's worth spending its processing power on. Is there like a ranking system that helps it prioritize?
Exactly. It assigns weights to different parts of the visual input. The areas that are seen as strategically important get higher weights, meaning the model pays more attention to them. And these weights are always changing as the game progresses so that the AI is focused on the most critical parts of the battlefield.
So it's not just reacting to the immediate situation, it's anticipating threats, looking for opportunities, and trying to make moves that fit into a larger strategy, like thinking ahead.
Yes, precisely. And this ability to selectively pay attention lets the model work efficiently, even when there's a ton of visual information to process.
Okay, we've talked about how the AI sees and makes sense of the game, but what happens next?
The next module is called knowledge integration, and it tackles a really important part of intelligent decision-making, using existing knowledge. Imagine a human player looking at a strategy guide or remembering their past experiences to make a decision. That's essentially what this module allows the AI to do.
So it's not just going off what it observes during the game, it's pulling in pre-existing knowledge about the game's rules, the strengths and weaknesses of units, effective strategies, and so on.
Exactly. And this knowledge is woven into the AI's decision-making, helping it make smarter, more strategic moves. For example, it can use its knowledge about unit counters to choose the best targets or use its understanding the map terrain to position units in advantageous spots.
This knowledge integration part seems really crucial to help the AI go beyond simply reacting to what it sees and actually grasp the deeper strategic aspects of the game.
Absolutely. By combining visual perception with a whole library of strategic knowledge, the AI can play the game at a level that approaches human-like understanding and strategic thinking.
So it sees, it thinks, and with knowledge integration, it strategizes. What's the final ingredient that brings this all together?
The dynamic role assignment module, and that's all about coordinating the actions of multiple units, kind of like a human player commanding an army. This module doesn't just see each unit as an individual, it assigns roles and responsibilities based on what's happening in the game.
So teamwork, essentially, working together to reach a goal. But how does the AI figure out which unit should do what?
This module looks at a bunch of things, including the type of unit, what it can do, where it's located, and the overall goals of the strategy. So, for instance, it might decide to use a group of Marines as harassers to disrupt the enemy's resource gathering, while assigning a squad of siege tanks as the defensive line to protect a key spot on the map.
That sounds like a complicated balancing act, constantly changing the roles and assignments as the battlefield shifts.
Yeah.
Can the AI adapt on the fly, like if the enemy makes a surprise move or the overall strategy needs to change?
Absolutely. That's one of the most powerful things about this module. The roles aren't pre-programmed, they're dynamic and constantly adapting to how the game is flowing. The AI can seamlessly switch units between attack, defense, and support roles as needed, making sure its forces are always being used in the most strategic way possible.
Okay, so we've covered the three big parts of VLM attention: visual perception, knowledge integration, and dynamic role assignment. How did these pieces actually come together to create an AI that can play StarCraft II so well?
The real magic is in how smoothly these modules work together. They're constantly feeding information back and forth, updating their understanding of what's happening in the game, and adjusting their actions accordingly. The result is an AI that can react to threats and seize opportunities, but also plan and execute complex strategies, just like a skilled human player.
It's incredible to see how far AI has come in playing a game as challenging as StarCraft II. But we're not just here to talk about games, right? The potential of this research goes way beyond the virtual battlefields of StarCraft II. What are some of the real-world possibilities for VLM attention and the techniques it uses?
The potential is huge, really exciting. The basic ideas behind VLM attention, understanding what you see, integrating knowledge, making smart decisions, they can be used in all sorts of real-world situations. Think about robots that can navigate complex environments, understand what humans are telling them to do, and complete tasks with a level of independence and adaptability that we've never seen before.
Like taking the strategic genius of a top StarCraft II player and putting it to work in robotics, automation, all kinds of fields.
Precisely. Or think about self-driving cars. They need to perceive their surroundings, anticipate what other drivers are going to do, and make split-second decisions to stay safe and get where they're going. VLM attention's ability to process visuals, understand context, and make strategic choices could completely change how we design and build self-driving systems.
It's fascinating to imagine a future where AI isn't just a tool, but a real partner, working alongside humans to solve tough problems and make our lives better in countless ways. But I think we're ready for our Novel Notions segment now, where we push the boundaries of what's possible and explore the future of VLM attention and the field of AI as a whole.
Definitely. We're just scratching the surface here.
And we are back for the third and final part of our look at VLM attention.
Back for more on VLM attention.
We've dug into how this system works, its amazing performance in StarCraft II.
And now it's time to let our imaginations run wild, to enter the Novel Notions zone.
Exactly. This is where we take the core ideas from the research and try to picture them in the future. Think about how they might be used in unexpected, maybe even game-changing ways.
Let's stretch the possibilities of VLM attention, explore some applications that are speculative but could be really transformative.
Hit me with your best ideas. I'm ready to be amazed.
One thing I find particularly intriguing is the idea of merging VLM attention with brain-computer interfaces.
Brain-computer interfaces. Sounds like we're stepping into science fiction territory here.
It might sound futuristic, but this field is making incredible progress. Imagine a system that can connect directly with our thoughts, our intentions, and then use VLM attention to turn those thoughts into actions in the real world.
Whoa, okay, so are we talking thought-controlled robots, prosthetics that respond to our brain signal?
Exactly. Instead of relying on physical controls, we could potentially interact with machines using just our minds.
That's a whole new level of accessibility, a huge shift in how humans and machines interact. What other possibilities are out there?
How about using VLM attention to develop AI that can truly understand and respond to human emotions?
That's a fascinating idea. AI therapists, AI companions that offer emotional support.
Yes, or even AI artists creating works that evoke specific emotions in those who experience them.
So AI that can connect with us on a deeper, more human level. That brings up so many questions about the nature of creativity, empathy, the future of how humans and AI will relate to each other.
These are just a couple of examples, of course. The potential applications of VLM attention are immense, a lot of uncharted territory to explore.
It's exciting and maybe a little intimidating to imagine a future where AI can perceive, understand, and interact with the world in ways that we used to think were uniquely human.
But like with any powerful technology, we have to be careful, thoughtful about the ethics.
That's crucial. As we create AI that gets closer and closer to human intelligence and behavior, we have to make sure it aligns with our values, that it's used to make society better, not worse.
Transparency, accountability, and human oversight, those are going to be essential as we navigate this new landscape.
Well said. We've covered a lot of ground in this deep dive on VLM attention.
From a new way to approach game AI to its potential to transform all sorts of fields, this research really gives us a glimpse into a future where AI can work with humans, extending our abilities in incredible ways.
It's been an eye-opening conversation. A big thank you to our expert for sharing their knowledge and guiding us through the ins and outs of VLM attention.
Happy to be here.
And to our listeners, thanks for joining us on Talk Tensors. We hope this episode has sparked your curiosity and got you thinking about the future of AI.
If you want to take a closer look at the research, there's a link to the paper in the show notes.
And if you enjoyed this deep dive, don't forget to subscribe to Talk Tensors for more explorations of cutting-edge machine learning research.
Until next time, keep exploring and keep learning.
That's all for Talk Tensors. We'll catch you on the next episode.